相对来说怎么？哦，会吧？关键的。
太好。好，我们开始上课。今天我们第一次课。我叫周阳，物理系。我的办公室在江湾。这学期我来讲这门课。这门课的题目是，名字叫做量子场论。可能有的同学都听说过，也了解一些，可能也学过一部分的知识。OK， 我看今天来的人不是来了很多人啊。那我们要不首先大家自己认识一下，快速的从这第一排开始，让我了解一下是本科生还是研究生还是几年级的。从你开始吧。OK。叫什么名字 ？OK。
我叫罗一晨，然后是研一。
你要说你是助教 ，OK。OK， 快一点，我们节省时间啊。
我叫陈梦宇，大四。我是黄宇。
我1年。研一。
我是李梦天，研2。我是张志范，大4。我是谭凯林，大4。我是吴一志，大4。我是李展军，大4。于一起大4。
刘正研一，学号想大2。
哦，不是2年级 ，OK。
研2。
陈瑞清，大4。
外系的报一下系名啊，我知道有外系的。
张元，然后博尔修佐的。
叶大4。何瑞。
于章大。
研2。
有一点眼三项目组。
大3。
汪岩，大4。
李明义，博士。 上大生不是较好的，杭州大厦。
本科3年级。还有一个。
我是节约大四。
OK，我们看本科的同学比较多，主要是4年级的啊，本系的，当然也有不少外系的，像现物所的。那从选课名单上看，我们看好像还有一位化学的，有一位数学的。总的来说，大家都有各自不同的背景啊，希望能够从这个课里面都能够收获。OK， 所以刚才说了这门课的名字是量子场论。那有一个重要的事情要介绍一下助教啊，因为你们很多要跟助教打交道，你们问问题也好，交作业是吧？都要跟助教打交道，所以你们把联系方式写在上面。好的，大家可以记一下。当然我的这个黑板怎么老是动？Office hour 是每周5的上午11点。大家有任何问题可以去找我。Friday。你也可以 email 你。还有一个信息就是关于这门课的 textbook。那么我们有很多 textbook， 实际上去年我这个也有讲课的视频在 B 站上，你们可以去看。对，这有一个好处是，如果你有兴趣的话，你可以先了解一下，比如下一节课的内容。这样的话，我们可以抽出更多的时间来回应大家的问题或者讨论。其实这个环节是非常重要的，以避免呢就一个人讲，这样也很无聊啊。所以教科书也有很多很流行的 textbook。那么我们总的来建议大家的TIC textbook 是，当然第一个是非常著名的 Paskin。当然，另外也有本比较现代的，叫马去 Schwartz， 也写的相当不错。比如在 Harvard 的，据我了解，很多年他们一直沿用这个场论教材。OK。那么当然，这个教材都有不同，每一本教材都有不同的特点，是吧？比如这个 Schwartz 的教材的话，它的 structure 的会显然比 Pascal 要好一些。就先讲什么，再讲什么 ，OK？ 这样一个顺序，而不是让你，特别是对初学者一上来一看，基本上每个 chapter 都像一个小书，就不知道这是为什么堆在一起，是吧？没有这种逻辑。所以这2本教材互补呢，应该是一个相当不错的选择。那么，如果为了加深比如物理的理解，那么也推荐这个有一个华人物理学家徐一红写的这个Quantum Field Theory in a Large Share。那还有一个另外还有一个相当不错的，所以我得先写这个，otherwise doesn't work。另外有一个相当不错的就是这个 David Tong， ，Cambridge 这个 physicist， 非常擅长于物理教学的 ，OK， 和演讲。他的lecture notes 都 publish 在网上 ，OK， 你可以直接 Google 就能找得到 ，OK。他名字叫 David Tong， 还有 online lecture notes。当然，还有一个大家也很熟知的 Weinberg，OK。那如果你仍然有剩余的时间的话，我们也建议你可以去参考Steven Weinberg，比如 Volume 1。OK， 这是关于这个课程的教材，有没有任何问题？有没有什么问题？
这样课还是会按照上学期的那个。
基本上是对，但是就像刚才说的，我们争取能够加一些新的比较现代的内容和一些讨论的环节，这样的话避免我们 repeat。Otherwise， 有同学可能觉得，哎，我去看 B 站就行了，是吧？为什么要来上课？为什么要来上课？当然有一个问题就是课堂跟这个你看视频，特别是这个去年我们学校的这个录制的这个系统还不是很完善。比如说我去年最后一节课直接就被消音了，一点声音没有。然后在 B 站上还被这个阅读了几千次，是吧？感觉就非常的尴尬。然后去年第一堂课也是这个声音就听不清。所以我建议大家还是来听课，参与讨论，这样的话理解会深刻一些。OK， 如果这是教材没问题的话，我们当然有一个很重要的问题，就是这个成绩。那么按惯例成绩的话，我们是problem set 是占40%，也就是做的作业 ，OK。然后我们有一个midterm 的 exam，OK， 这个是20%。当然，我们剩下的就是 final exam，OK。这是我们这个课程的成绩组成 ，OK。那么根据去年的情况呢，这个有同学这个平时也没有来，也没有交作业，然后期中考试比如说又因故就缺考了，然后后来又申请了缓考，这样的话就非常难以 pass， 就是你这个成绩就没有这个组成部分，就是所以大家注意一下啊，这个我们都是非常客观的按照大家提交的东西评估的，和最后你考试的卷面，我们的就是说，但我们最后评估的时候就是说，我们只要找到任何一个理由，觉得你 qualify 应该让你通过，一定会让你通过 ，OK。但如果我们实在找不到，那就比较麻烦 ，OK。比如说一个 case 就是说，当然跟大家透个底啊，比如有的同学可能平时没有什么成绩，但他期末考试就可以看出来他会了 ，OK， 基本的东西会了，比如说他考过了60或者70分，那我们根据这个一看的话，也会让你 pass， 但是不是建议让大家就是这样去冒险 ，OK， 就是这种特别情况我们会仔细看他的 这个考试的情况 ，OK， 卷面成绩结合。那么如果你没有那么 confident， 最后的期末考试建议你中间的成绩要注意一下啊，补起来。平时成绩和这个期中的，期中我们通常的考试比较简单，就检查一下大家基本知识掌握的情况。OK， 期末考试可能会难一点，考核一下看大家会了没有，这是大概的情况。然后还有一个事情，对于成绩有什么问题 ？OK， 没有问题。我看了一下这个注册的选课的名单，然后我发现了有1、2、3、4、5、6、7，有7个同学好像没有加入 e-learning， 大家一定要加入 e-learning，otherwise 这个评估作业和交作业是非常不方便的。OK， 特别是外系的同学。如果你要选这个课，我不知道有几种可能啊，是旁听也好，是选也好，是什么样也好，什么是你得进入 e-learning， 如果你要交作业的话 ，OK。因为我发现助教到时候去注意一下 ，e-learning 上好像有8个人，这上面有8个人 ，e-learning 上没有 ，OK。我不知道是出了什么状况。比如这个是有一个数学，有2个强基的，有个英才的。还有一个普通的，还有一个修双学位的，e-learning上都没有名字。对，你们回头去加一下 ，OK。OK， 这是，然后还有一个，这个其实不用讲，我们课的这个预修的知识要求是这个，当然这个量子力学，大家都学过量子力学吗？没有学量子力学的举手。没有学量子力学的举手。没有 ，OK， 很好啊。然后我们要有这个狭义相对论 （special relativity）。当然，这个 classical mechanics 也是有用的 ，OK。当然 assume 大家都会了，是吧？这是一些预备的知识。然后这是关于这个课程的一些基本的信息。大家有什么问题？然后我们没有问题就正式开始上课。正式上课的时候我们用英语讲，大家有没有问题？因为这是个高级课程以前有研究生说这个可能听不习惯英文，之前可能没听过是吧？但是我建议的话就是说，像这种高级课程，大家要习惯communicate in English， 否则的话，你到时候做研究，特别你要做学术的话，实际上无论做什么，你即使不做学术也是有用的。你要跟别人交流的话 ，OK， 你要熟悉这个语言。所以我们可以趁机在学校的时候就把这个 get 到 ，OK， 就适应下去 ，OK， 这是非常重要的。OK， 那我们就开始上课啊。I will first do this board, and then this board. Okay. So we are going to discuss quantum field theory. Then the most important question is why we care. Okay, why we care is something called quantum field theory. Do you have any idea why we should care quantum field theory? Does anybody can say something? But you might say, okay, I don't know what is quantum field theory, so you can't ask me why, right? Okay. So quantum field theory is important in a sense. You cannot avoid it, okay? You cannot avoid quantum field theory. At least by now, we don't know. There's other replacement for quantum field theory if you try to combine quantum mechanics and special relativity. So in this sense, quantum field theory is a result or is a consequence of quantum mechanics plus special relativity. Yeah, this is important. Yeah, it's unavoidable. Okay, it's unavoidable. In history, there's an interesting history here because naively, if somebody asks you, I guess everybody knows what is non-relativistic quantum mechanics, right? That's what you learned. Now, if somebody asks you, what if you try to make this non-relativistic quantum mechanics like relativistic, okay? Then you might naively say, okay, I should invent something called the relativistic quantum mechanics, right? Sorry. Right. This is the problem. You see, if I do this first, this second, it's still second time you have this cannot be seen. You see. But anyway, what can I do? I will just maybe I will skip this second board. Only do this board. Okay. Good. So first, why QFT? First, QFT is a result of quantum mechanics plus special relativity. Okay. As said, if you naively put these two together, you might invent something called relativistic quantum mechanics, okay? Is that okay? So what do I mean by this? So in non-relativistic quantum mechanics, you learn something called the Schrödinger equation. Remember this? Okay, it's very familiar, right? So if someone asks you to make this as relativistic, what you should do? What you should do? So you should first try at least. You should see, because this equation is this E equals to P squared over 2M, right? Right? It just translates the dispersion relation to differential operators and act everything on the so-called wave function. Okay, so you get a Schrödinger equation. Now, certainly this is not a relativistic. Okay, it's not a, for example, it's not a Lorentz invariant. So to make this as the relativistic one, instead you should use the relativistic dispersion relation, right? E squared equals to P squared plus M squared. Okay? Then again, you translate everything into these differential operators act on something might be called the wave function. Then you can write down the relativistic version of this Schrödinger equation. So if you do so, what you get? Okay? People already tried it, okay? People already tried it in history. They wrote down some equation looks like this. Okay? So what is this equation? There's a famous name for this equation. That's right. This is the so-called Klein-Gordon equation. Okay? This is the Klein-Gordon equation. However, this is a little bit too naive, okay? In a sense that if you try to push, start from this equation, do similar analysis as what we did in the non-reduced quantum mechanics. For example, try to find the probability density interpretation. Try to justify whether this probability is conserved, okay? Which is positive and conserved, you cannot find such a candidate from this equation. Okay? A simple mathematical fact. Okay? It's impossible to find. Both non-negative or positive, as well as conserved probability density. Okay, remember that in quantum mechanics, how do you understand this wave function? You put psi and psi star, right? Psi and psi star. This measures the probability density. Okay, at some points, right? That's the interpretation in quantum mechanics. However, if you try to do similar thing for this equation, you can't do so. Just simply cannot find a good candidate, both positive and also conserved. Okay, because we know probability or probability has to be conserved and probability density has to be positive. Okay. So it suggests, it indicates already something sick for this naive speculation, right? So in fact, this so-called relativistic quantum mechanics does not exist, or you can call it sick. Okay. It doesn't make sense, okay, to construct such a theory. So, So this reason looks a little bit technical. There's in fact a more fundamental reason, if you think about it carefully. Why we cannot find something similar to Schrödinger equation, which is also relativistic. What is the reason for that? So fundamentally, if you think about a particle, for example, what do we mean by push to the relativistic regime? Just means that the speed of this object is very high, right? For example, close to the speed of light. Okay. You boost it, you let this object move very fast, okay? If the velocity is fast enough, then this particle will carry a lot of kinetic energy, okay? You see? So we know there is some energy coming from, for example, the rest mass. Okay, some energy comes from this kinetic part. Okay, the kinetic part is dependent on the velocity. If you boost the particle to very high speed, then there is a huge amount of kinetic energy. Okay. So if that happens, actually that kinetic energy can be transformed to some mass or some other particle, okay, in relativistic world, okay? It's allowed, okay? If the energy is big enough, it just can turn to, for example, 2 more particles, okay? So that's the fundamental reason. This means that particles can be born and also die, okay? This means what? This means the probability for a fixed number of particles, which what will made established as a concept, right? Very important or basic concept in the usual quantum mechanics does not exist. Okay, because the number of the particle is not fixed anymore. Okay, so it's no sense to talk about a single particle wave function or two particle wave function or three particle wave function. Okay, because particle number can fluctuate, okay, can change. So this leads us to, so we have to think about a new concept, or we are led to the new concept, field. Okay. So I have to think about a new concept, something called field. But this is not new at all, right? We all learn, even in college physics, even high school, we know there are a lot of fields around us, right? That's what already very extremely familiar, right? So what is the typical field around us? What is it? That's right. Maxwell field, right? Maxwell field everywhere, right? Whenever you see light, you see it. So this gives the third reason. If you believe our fundamental world are all should be quantized or quantum mechanical path, okay, then you have to seriously think about a basic question: how do you fit our understanding of the light, okay, of the light in high school? How do you fit that understanding into quantum mechanics? Okay, if you believe, okay. So this means that quantization of our familiar classical field, like electromagnetic field, or magnetic field, this this also gives quantum field. Right? We are physicists. You cannot you have to be serious, right? Right? This if you agree that everything has to be quantized, then this familiar field has to be quantized. Then you should seriously do so. Then this leads to also quantum field theory, which means that quantum field theory is relevant to our world. How to deal with this. Now these are all the it seems they are all fundamental reasons, right? We are always by now asking the fundamental questions. But if you are condensed matter people or solid physics people, there is actually another reason, or even statistic physics. Okay. No matter you're working in condensed matter or solid or statistical or even experiment, okay. Actually, it's better to have a bit knowledge of quantum field theory to understand what you're doing. The reason is that quantum field theory also quite often emerges as the continuum limit of some discrete system or lattice, okay? Discrete or lattice. You see? For example, in solid physics, we always deal with lattice, right? Where you have a lattice, no, the atom here, but they're just laid in some lattice. The point is, if you have a lattice system, okay, for example, you can try to think about, you take this, the lattice distance, okay? A, for example, this lattice spacing, or sometimes called, if you take this A goes to zero limit, then the system becomes effectively a quantum field theory. Okay. Now, if you learn something called RG flow, I mean, I assume you, because in your statistic course, you can easily realize that there is a more serious picture to see this, right? For example, in the UV, there's a lattice. Then, if you try to perform some coarse graining, okay, or RG flow, then you flow to the infrared, okay. Sometimes it just becomes some theory or some fixed point, which looks like a quantum field theory. Okay. It just means that you know you measured some scale, very macroscopic scale. Okay. Okay. Depends on your measurement. Okay. If your measurement scale is huge compared with this lattice spacing, it's equivalent to this, say, this lattice spacing goes to 0, right? You see it? Then the system becomes continuum. Then the quantum field theory emerges. The quantum field theory also emerges from lattice system or discrete system. Okay. So it's not only a matter of fundamental world or particle physics. It also matters in condensed matter physics. Okay. Actually, it's very powerful, at least for theoretical condensed matter community. Okay. Yeah, there is a concrete examples, but maybe yeah, let me. Okay, we can leave this later. Okay, so these are the motivations why we care quantum field theory. Are there any questions for this part? Okay, so now we come to the question what? What is, right? What is? What is quantum field theory? I cannot stop it. What happened? It was designed like this. Maybe some magnetic force. I don't know. What can I do? I will just escape this problem. So what is quantum field theory? Of course, the whole course is going to answer this question, right? So it's impossible to answer within these few minutes. Okay. But nevertheless, we should try to get some feeling, okay, or a global picture, or what we are doing, okay. Now and then we are going to great details, step by step, okay. So what is quantum field theory? It's a big question, right? It's a big question. Roughly, you need 10 years, or even more. Okay, maybe 20 years, if you want to answer this question. So very roughly, so we mentioned already here, we have to if you want to quantize the classical field, okay, these are called the classical fields. Okay. These are called the classical fields. If you want to quantize classical fields, you have to go to quantum field theory, right? So there must be a relation between classical field theory and the quantum field theory, okay? Like a promotion, okay? How do you promote a classical field theory to a quantum field theory? Okay. So very roughly, quantum field theory just means if you give me a classical field theory, for example, a very simple classical field theory, like phi xt, okay? Phi xt, okay? By now you can think just this is a function, okay? It's a function of space and time, okay? It's a function of space and time. Later we will see something like this called the scalar field, okay? Okay? But the point is, in classical field theory, this is just a function, right? It measures some physical quantities at every space-time point, you see? Because that's what this function tells, okay? Now, in quantum field theory, this classic function now becomes an operator. Okay? Remember that. So what is the operator? What is the operator? Is there anyone who does not know what is the operator? You should know what is the operator in quantum mechanics, okay? Because in quantum mechanics, we introduce a very important concept called the Hilbert space. You see? Right? Hilbert space is formed by all the possible states, right? That's the Hilbert space, okay? Now operator is you can view this as a matrix, okay? In this vector space, right? That's what we call the operator, okay? Operator transform. If you act operator on some state, then you get another state, right? So in that sense, operator does the job to transform from one state to another. So that's the operator. Now the point is now you have to keep this in mind, okay? Very roughly, quantum field theory just does this very simple like job to promote this classical field like a function to an operator. Of course, in a sense, the operator has to stay in some Hilbert space. Okay, then there will be also a Hilbert space for this quantum field theory. Okay, and now maybe this is not concrete enough to you. Then more concrete way to say this is now phi becomes something looks like something I denoted as phi hat, okay? In order to indicate this is really an operator. So now this phi hat x now becomes this phi hat xt. Now what is this? This is some operator valued. Function of space-time, okay? Okay. So make a comparison, for example, as said, from classical field, if you promote this phi to an operator, you get quantum field theory. Now, we're all familiar with quantum mechanics. Actually, there's a nice way to try to compare quantum field theory and quantum mechanics. Okay, term by term. Okay, term by term. For example, in quantum mechanics, we can view this x, okay, position. We can view this x as a position operator, right? That's what you learn, right? X can act on some states, right? So x hat is the operator. So x hat, x is just the coordinate position, okay? Variable, position variable. So x hat. Now, analog to this x hat in QFT, as said here, we have operator instead of this x. We actually have the phi. We view the phi as an operator. So phi hat, but not this x anymore. Okay. So phi hat. Now, actually, now there is a slightly you have to distinguish here. So whether you allow your operator depend on time or not. Okay. So what's the difference if you include the time dependency into your operator or not? Do you know that? What's the difference between these two choice? Do you know? If you allow your operator has time dependence, which means we're working in which picture? That's right. This is the Heisenberg picture. There are two completely equivalent pictures in quantum mechanics, okay? In one picture, we call the Schrödinger picture, we include all the time dependence in the states, okay? In Heisenberg picture, we include all the time dependence in the operator, okay? Then you have two choices. Later, we will see quite often we will just include the time dependence, which indicated here, T, okay? There's a T inside this operator, which means the operator has time dependence. But if you insist, I like to work in this Schrödinger picture in quantum field theory, that's fine, okay? There's also something like this, called like this. Then you should erase this T, right? That's it, okay? You should erase this T, that's it. Now, compare these two, you realize that in QFT, X is no more an operator, okay? X is no more an operator. Instead, since phi is an operator, now phi is also a field, right? You see, phi is also a field, is also an operator. So it just means that the X becomes some index, right? Labeling. There are many operators, right? You see. Because phi as an operator, it depends on X, right? X is not operator, it's just some labeling, it's some index, okay? So that's what you should think about, yeah. So what do we mean by an operator valued function, okay? Operator valued function, okay? Means this, you can try to lattice your space-time, okay? You can lattice your space-time, you can think about at each point there's an operator located there, okay? Now there are many operators. They are labeled by X, okay? Then promoting to the continuum limit, we call this is a operator valued function. Now we also call, by the way, 就是我们现在下课的时间，我们争取每次上课中间只下课休息15分钟，有没有问题？否则我们一会儿下课可能就要听很久。大家有没有问题？所以我们大概讲一个 story， 中间就可以休息一长段时间，是吧？也很划算。Okay. So we also have some notion like a state. So in quantum mechanics, as you all know, if you are talking about a position eigen state, okay, we just write it in this way, right? Use a cat, okay? Use a cat, X, put X inside. Now, so make this similar in QFT. What you should do is something like this, okay? Something like this. Yes? Oh, okay. Okay, thank you. So you should make this right? It's completely analog to this, right? Because it just means you should put the eigenvalue for your operator inside this cat, okay? This can mean the state, okay? That's what we mean by state. And even wave function, we are familiar with, right? This is maybe most familiar tools in QM, in quantum mechanics, is the wave function, right? So wave function, for example, we label this wave function. We label this wave function by psi, capital psi x. Now what happened here? In quantum field theory, you can also do so, but don't forget. Now, the variable inside of this wave function now becomes the eigenvalue of the corresponding operator, which is phi itself. Okay? So this means what? This means in quantum field theory, in order to understand some concept called wave function, you have to think about looks like a complicated object, mathematical object, right? This is sometimes called the function. This is the function null. Okay? This means that this is the function null of some function. Okay? So phi itself is some configuration, for example. Okay? Because phi itself is a function. Okay? Okay? Now you have to deal with the function null of a function. Looks like complicated. That's the reason why people usually we don't use this wave function tool in the quantum field theory. Okay, instead we heavily use the Heisenberg picture as said. Okay, and yeah, turn to some other more convenient tools. So I hope now you get a little bit feeling of what is quantum field theory, right? It looks like a complicated framework, and complicated in a sense. Now this picture is I think is very convenient for you to understand. The practical degrees of freedom in quantum field theory, okay? Whenever you have some confusion, you don't know how to count degrees of freedom in quantum field theory, I suggest you turn to this picture, okay? This picture is just a lattice, okay? Now you think about, you take the lattice space and go to 0, means you go to the continuum limit, then the quantum field theory emerges, okay? Okay? Or put it inversely, you can think about you lattice in your quantum field theory. Okay, it now becomes some the usual lattice system. Then in lattice system is very easy to understand, right? You can think about there are lots of degrees of freedom on each side. Okay, on each side you can add there are atoms or particles at each side. Okay. Okay. So if you keep this picture in mind, we can give a very rough definition for quantum field theory. By now, you can see quantum field theory is a framework. It's a framework for what? It's a framework for incorporating an infinite number of quantum degrees of freedom arranged in space-time. Why we call it arranged? This word means that the space-time now becomes some index, okay? Because these degrees of freedom, think about a lattice. They are arranged in space-time, okay? It's distributed over whole space-time, okay? There are a lot of degrees of freedom, okay? A lot of particles, not only one or two, okay? There are many, infinite. Arranged in space-time now later we will try to add also interactions. So this framework can incorporate also interactions. So with the interactions, of course, these interactions are not arbitrary, okay? These interactions are highly constrained, okay, by some principles, okay? So there are lots of infinite amount of degrees of freedom distributed over space-time. Of course, there could be interaction between the degrees of freedom, right? Right? There could be interactions. Now the point is these interactions are not arbitrary. You can add whatever you want. No, the interactions had to follow some principle. Okay. In other words, they are constrained by some principles. Okay. Constrained by what? Constrained by the following principles. First, locality. Okay, locality. Locality. Next week, we're going to discuss in great detail what do we mean by locality mathematically, okay, or in the equation level, okay. Locality. So now we'll just introduce this principle in words. This locality means that all the interactions happen at points. Okay. Which means what? Why this is important? Think about it. Interaction means someone can touch another one. Okay. If you relax this principle, then, for example, you consider some interaction which is non-local, okay, which is non-local, then you can violate, for example, some, you can get some strange behavior, because this means that the interaction or communication can happen faster than speed of light, right? Which is acausal, also violate causality. Some weird non-locality also violate causality. Okay? So locality is important. Think about your Maxwell equation. We're going to discuss it next week. But now, in order to understand what do we mean by locality, think about the Maxwell equation. Remember Maxwell equation? You can write down Maxwell equation in terms of differential equations, right? Right? But the point is that if you look at carefully these differential equations, okay, they are all happens at the same point. You see? You see? The operators are all act on the same point. Okay. For example, this Maxwell equation in terms of E or B field, you can write down to check it yourself. Anyway, we're going to come back to this to discuss this in detail again next week. So don't worry. Another is very important. Also, I think maybe also familiar for some of you, is symmetry. Okay. Yeah, we all know symmetry are important, right? So we have great physicists, Li and Yang, a giant in this field of physics. Yeah, all the experts on this symmetry. So, for example, in today's course, we're going to cover the Lorentz group, which represent the Lorentz invariance. So symmetry, this space-time symmetry, for example, Lorentz invariance. So later in this course, we're also going to touch something called the gauge invariance. Okay. So following these symmetry principles, you can construct a different series. Okay. So this QFT, if you want to construct a concrete theory, okay, quantum field theory, okay, you have to pay attention to all these important principles. So there are also important property called the unitarity. Unitarity, okay? So what do you mean by unitarity in quantum mechanics? Do you know what is unitarity in quantum mechanics? Unitarity just means the probability has to be conserved. Okay. Okay? The probability has to be conserved. It cannot flow as time goes by, right? in quantum mechanics, quite often you are dealing with something called a unitary operator, okay, or unitary evolution. Do you still remember? Okay, all the time. For example, the time evolution operator has to be unitary, right? Why? Think about it. Why? Because unitarity, okay? Because you cannot change the probability. Probability has to be conserved as time goes by. So this flags to the unitarity. So unitarity means the probability conservation. The last is something called causality. Okay. Causality is even we know what is this, right? Even from middle school, right? Causality just means everything has to be causal. You cannot travel faster than light. Okay. So no faster than light influence. What we call the causality. Again, we're going to come back to all these four principles in the later weeks. Okay. For example, to make this is very clear in quantum field theory, we're going to use the commutator. Okay. To make this causality very precise. For example, if two operators are located in 2 points which are space-like, okay, they have to commute. Okay, that's the more mathematical statement for the last condition, which is causality. Okay, but if you think about it carefully, it's the same thing. It just means there cannot be faster than light influence, right? Okay. So these are the important principles QFT has to follow. But of course, there are some, whenever there is a restriction or constraint, there is something go beyond, right? That's always happen, right? Of course, you can try to write down something even go beyond this one, something non-unitary, even non-Lorentz invariant, of course you can do so. But in this course, we are going to restrict to this, okay? We only talk about this series, satisfy these constraints. Okay. So they are constrained by these four principles. So this is a one-sentence definition for quantum field theory. Okay. If you like, you can remember it. Okay. QFT is nothing but a framework can incorporate or describe infinite number of degrees of freedom that are arranged in space-time. Okay. They allow the interactions, but the interactions should satisfy some principles, okay, physical principles. Yeah, that's it. Okay. So this is a very short introduction for what is quantum field theory, for why we care quantum field theory, and what is quantum field theory. Are there any questions about this short introduction?我们可以用中文提问，没问题的啊，讨论也可以。
就是那个 QM 和 QFT 的那个算法。意义。就是你X 那个算符嘛，然后在那个 QFT 里面是那个 phi， 就它的物理学。
Okay, good, very good question. Okay, very good question. Now let me try to answer your question because I precisely skipped some part of this. Yeah, thanks for the question. So indeed, it has some very definite physical meaning. Okay. For example, we mentioned somewhere here, the QFT can emerge from some discrete system, right? But we skip the details. But now let me try to go back to that one. For example, if you think, you can think about write it here. You can think about an example. This example is very famous and is important example. It's some 1D chain of oscillators. Okay, what do we mean by 1D chain of oscillator? Looks a fancy name. If you're not familiar, it's okay. It just means, you see, there's some spring, okay? The spring, okay? And there are some particle or atom, for example, okay? And this line is infinitely long, okay? This is called the 1D chain of oscillator, okay? Okay? 就这儿有个原子 ，OK， let me explain 这儿有个弹簧 ，OK， 然后你考虑这个无穷长的 ，OK，very simple, right? You can write down the Lagrangian, classical mechanics, whatever you want, okay? Whatever you want. So let's try to do that. Now think about this is called previously we called this lattice spacing, right? This is lattice spacing parameter A. Now there is for each one coordinate you can also label. For example, this is as some x. This is some x. No, let's don't do that. Okay, a minute. I should be careful with my notation. Yeah, this is lattice spacing. Now you can think about now. For the coordinate of each atom, for example, the nth atom, we have xn, okay? We have xn. Now, since this position of this atom can fluctuate, right? They can move, right? They can move from a bit to left or to right, okay? Which means this xn can shuffle from its origin position, right? So this is emerges a new variable. For example, let's call this eta n. So eta n is defined as some xn minus sxn at the original point. Okay. So this variable measures how each atom, okay, live away from its original point. Okay. Now you can write down the Lagrangian for this variable for this system. Okay. For example, L equals to, we all know this equals to T minus V, right? Kinetic energy minus potential. Okay. T minus V. So you can make this is very precise. For example, this is n. This is the half. If you think about it, the mu is the mass. So this is the eta n dot square. Yeah, you can also make it clear for some interactions and also some potentials. Right? Carefully analyze this chain of oscillators, then you find this mechanics. You can write down this one, right? This is by now, this is the sum over n, so this is for a discrete system. It's very precise. You just describe how a chain of oscillators moves, okay? Now you can do the continuum limit. For example, you can take a goes to 0, okay? Now you can change your discrete variable n, then now n you can change it, it becomes small x, okay? Because when it goes to continuum limit, then n disappear, right? N goes to x. Now what? Now this sum, now you can carefully work out this discrete sum or this Lagrangians. Now this sum becomes some integral. And eta n, importantly, now eta n, now you can realize that this becomes some variable. For example, you can label it as eta as a function of x and t. Okay? See? Now you see the field, the one-dimensional field, two, because this is okay, 1 plus 1. So the field emerges, okay, in this continuum limit. So in this concrete example, answer his question. The eta field measures your oscillator, the shuffling of your oscillator away from the original point. Yeah, that's it. So the answer is yes. Yeah. There is a definite physical meaning quite often. That also happens in this electromagnetic field, right? We know what electromagnetic field measures, okay? So field variable do have definitely physical meaning, okay? Any other question? Yes.
就它那个是如果把那最后这个
Yeah, that's what I suggest you to do it by yourself. You should work it out. Yes. 没关系，用中文讲。
Silicon 的 quantization 里面有一个那个field operator. It looks like the operator in QFT. So they are
In which
quantization.
what quantization?
就二次量子化里面。
Second quantization.
那个它的这个 QFT 里的这个算法是一个。
Yes. So what's the question?
长得有点像。就二次量子化里面那个场算符和这个 QFT 里面这个算符我觉得长得很像，他们是有点。
That's a good question. But not the same, of course. But what's the relation? It's a good question. I think we are going to discuss this when really quantize this phi, okay? Using harmonic oscillators. You will see this more clearly. Okay. Any other question?
就是那个Lorentz那个地方，如果说相互作用项里面出现了导数项，就是怎么理解这个导数？因为导数项的话，它必然涉及不同点的那个场嘛。那你说，如果说这个相互作用项发生在同一个点的话，那相互作用项里面出现的导数项问题？
That's a good question. Only special derivative is allowed, as far as I know. Okay, time derivative is not allowed, right? Because then it becomes a causal, violate causality. So only special derivative is allowed. Even though special derivative is allowed, I don't think it's necessarily to be non-local. Here, by locality, what I mean is even though you include this derivative or higher derivative, whatever, higher derivative, let me say. The point is all the differential operator has to be act on the same point. Then it's still local. It's local, right? You can write down some theory with second order, second order for the t derivative, but higher order than the x derivative, for example. That theory is perfectly fine. This is still local. You can check it. Yeah.
Another question. When a is equals to 0 and eta n eta n加1 minus eta n is very, very small, and the second term is much, much smaller than the third term. If eta is continuous.
That's right. Yes. Is there a problem? Because that's precisely compensates the first term combined with right? Combined with the x derivative, you see? The second term contributes to x derivative. That's it. No, it contributes to x derivative in the continuum limit. Any other question?
occurs to me to that in optics.
Sometimes the media is spatial or dispersive, then in such cases the locality is broken, or
Can we?
write down the QFT analogously.
This is just a principle. As said, you can of course try to go beyond this. What I'm just saying is, if your theory satisfies these 4 principles, it's more nicer. It's a nice theory, but you can go beyond. But whenever you go beyond, whenever you have a constraint, you can go beyond, right? Whenever you go beyond, you miss something more exotic, some weird situation. But you can do you can do so for certain purpose. Yeah. Okay. So in the remaining time, what can I do now? 我们几点？我们是几点上的？9点55，9点55，10点。我们几点下课比较合适？Okay. So in the remaining time, we're going to cover 2 topics for today. Okay. One is because we said clearly QFT somewhere. I erased. I'm sorry. Here, good. I didn't erase. We said clearly QFT is a result of combining quantum mechanics and special relativity. Okay. So in the remaining time, we're going to cover 2 important topics. First, we will do this one. I will just try to remind you the key tools or concept in the special relativity. And then we're going to do one also key example to review the quantum mechanics. Okay? So we're going to cover 2 objects. One is Lorentz group. Okay. How can we get Lorentz group or understand the Lorentz group in special relativity? Another thing is how we quantize a simple harmonic oscillator in quantum mechanics. Yeah, that's the 2 things we're going to cover in the remaining time of today. Okay? So let me continue for the first. So first is the Lorentz group. This doesn't work. So. So is there anyone who does not know what is Lorentz group? Raise your hand. Any more? Only one person. Okay, very good. So in principle, I can escape this one, but just a quick remind, okay? Because this is so important. We're going to get to this review of this Lorentz group. So in order to understand the Lorentz group, you can think the simplest way to understand the Lorentz group is the rotation. Okay, it's just some funny rotation in the Minkowski space or the space-time. Okay, space-time. But it's not a big deal. It's just in a sense, it's just the same as the usual space rotation. Okay, what you are all very familiar. Okay, just rotate some points. Okay, in some space. That's it. So the important point or to understand this Lorentz group is the rotation. Yeah. Remember, always remember this is the rotation. Now let's start from the rotations. So the most familiar rotations is the 2D plane rotation, right? For example, this is your x, this is your y. You have some points labeled by x and y. Now I'm trying to rotate these points okay, surround this origin. Okay, let's try to do that rotation. Then if I do the if I do the clockwise, okay, this is anti-clockwise. This is clockwise. Okay, if I do clockwise by amount of theta, for example, okay, then I get another point, right? X prime, Y prime, right? You see? Familiar? So there's a linear relation between X prime, Y prime, and X and Y, right? Is that right? So can you work it out, this linear relation, in 1 minute? This is a middle school exercise, right? So what is the best way to work it out? Can anybody has any idea? Only idea is enough, yeah, because we don't have time for too much exercise. So any idea? Can anybody see some ideas how to work it out? This is a middle school exercise, right? For example, I can turn this x, y to polar coordinates, right? Change to variable r, okay? R and angle, polar coordinates, okay? Then rotation in the polar coordinate is pretty much easy, right? You just add some angles, okay? Then you use some relations of this cosine or sine, then that's it. You can work it out in 1 minute, okay? So we don't have time, but just let me work it out for you. So this linear relation or transform is just it's going to this kind of rotation is going to transform or send x to x cosine theta plus y sine theta, okay, and y goes to minus x sine theta plus y cosine theta, okay. That's the result. This is the result. This send means this means x. This means x prime. Okay. This means y prime. See? It means I send my transformation or rotation. Send one point to another. Okay. Now there's a nice way to package these transformations, which is also going to be very useful. So you can, if you are used to accept this kind of format, okay. So I can write these two equations, these are not equations, two transformations as send x, y to some 2 by 2 matrix, okay. Cosine theta, sine theta, minus sine theta, cosine theta, then act on x, y. It's not a big deal, right? This is easy for you, very easy. Now, I can equivalently also write this as into another form, okay? X and y is send x, y to x and y together with a 2 by 2 matrix, which is the transpose of this 2 by 2 matrix, you see? Because this is minus sign, this is sine, this is the cosine, okay? You see? It's completely equivalent, right? These two, completely equivalent. Or both does the job to do this transformation, right? Send one point under rotation to another point, right? Now, because in this course, we're going to deal with a lot of index sometimes, okay? So it's better to get familiar with those index notation. So this is the actual purpose of why we make this example very precise, okay? Starting from here, we will see and make it as an index notation. What will happen? So I can define abstractly. I can define this. This is called what? This is some column vector, right? Okay. This is a row. This is a column. Okay. We can define this as an index notation. As, for example, for this one, we can just write it in a more abstract way as xi goes to some matrix I, j, x, j. Is that okay? You see? I just use an index, so-called index notation. I use an index to label this first row and second row, okay? Of this column vector, you see? I just use another name, okay, for this object. So this is xi. Now it goes to this one, so this is a 2x2 matrix. I use another R matrix. As you use this one, this is actually represent the matrix. Now they have two indexes, okay? Two indexes. One is I, another is j. One is lower, another is upper, okay? Now act on another xj, you see? So this faithfully represent this transformation. Now similarly, I can do for this one, right? For this one. So write this one, what should I get? This will become the xi, send it to xj, r, t means transpose, and j, I. You see? Is it clear? Now you can easily check. There is a nice relation. There's a nice relation for these two rotation or R matrix. So what is that? Can you see that? So for the R matrix, there's a nice relation, right? So you can easily check that R transpose times R. This is the identity matrix. You see? You can easily check yourself. Because I already write everything here, right? This is the R transpose. This is R. Okay? Take product. You get this one. This means that this R matrix is something called orthogonal. Okay, such kind of matrix is called orthogonal. And you can also check another property of this matrix, which is the determinant of this R is also 1. Okay, you see? Check yourself for both. Okay, this determinant is also 1. If this matrix satisfies both these two relations, we're using some a more fancy name or labeling to label this transformation or matrix. We use the SO2. Okay, S means special, O means this is orthogonal. This matrix is orthogonal, right? And 2 means that this rotation happens in the 2D plane, right? This is a two-dimensional rotation. Okay. So SO2 is a group name, okay? How many of you learned the group theory? Quite good, okay? Huge amount, okay. So you should be familiar with this, okay? So that's why we call this 2D rotation group is the SO2. Okay, as explained. So this is a 2D rotation group. As said, Lorentz group is nothing but some higher rotation group in some higher space. That's it. So it's better to start from here, this simple, super simple example, and then promote to the Lorentz group. Okay. So OK， 我们休息一下吧，休息15分钟。
就是你不是骑的比我这走的比我早，
我这是个脑袋。
哦，这还有班会，还有班会，咋会？对，这个很多。就刚刚
啊，别人有他的方法，不想也都是靠。我们班都很细致的，全看方案是服务的。他去看之后会讲的是什么？会讲，就是他写的，会放开来。还可以是一个电影观众，跟啊，我就别是这个。
是吧？
大概
下发现434标准一目标。虽然那就是我知道，只有那个。那我一节课做就是好像可以讲来，就以后上学是正常的，回来了在上面是一个手用完线，没这反正真正我刚刚在而且都非常然后对，反正是别上了，我考虑去做。应该是这样，就是现在晃在讲，上的学员，特别聪明，这可能特别自由。
也是别人北部的一般啊，因为基本上可以这样做，这是我也给3.5的球队，1点的销售，其他收基本上个人见识，我都管啊。可以啊，甚至比较是听，比如说，他跳上给他经常也跟你少量的，一个是比较大的刀，就是有个最近在调研那个也是啊，也是有一个电子设备，教练这里应该是做一是可以，因为咱们山大那个。招门，这个感觉是稍后，本来发现你很行吧，多了，来挺好。哎，你意思我就是差不多了，就是一样，利润前景的非常清晰。那我就写出来一些其实想现在上面这种例子呢，其实还是特别虽然说会是像原始的就是前面下的脑袋特别才后面的修复其实在你可以去更大的时候你那种人的话还是解释信号用在原来我看就是有在其实他们说也有一些把答案发出去，我以前我不会写，直接光给扣吧，我也写工资给你扣吧，可以创造扣你。要扣1800，对，就是你现在 X 然后这个月全部大概就标3年不也月啊，你觉得其实很难，有是一起就到我这个因为是这个上都不贴感觉来说 QFT 知道吗？我到时候起头就把一点借条打了。体质，这个你写上来，以后记得的话，在北京跟200就可以。这个上一个是但是那只是什么时代？是的，是。我喜欢这一点而且，它其实现在毕业，你看都不是正常，对，而且就是说，在这儿
上网多。 一个是不是标准？嗯。我4年我从来没有这种中国的，让大家问。
就准备去那个是要去带我空的话，因为考这些老师，就考这些老师。不上周我刚才把那个给做那一期，但是对得到一个成绩，对吧？所以你真的是就是对让人想法，学一般都挺累，就他搞这些什么都应该产业而已。花都是
OK， 对于你们有的本科生说没选上课的，我刚才跟郭建云老师讲了一下啊，因为我们这次好像研究生选的不是很多，总的人数应该没有超，所以应该可以选，可以。OK， 那我们继续吧，抓紧时间，早点讲完。So where we are here. So this is a nice way to define the 2D rotational group. We can see it is SO2, right? Precisely SO2. There's another way. There's an alternative way. Another way to find this the same group, 2D rotational group. Okay. What is that way? Through the preservation of the norm. What do I mean by that? Maybe you already observed there is a very interesting relation. So we're talking about a rotation act on this xi and also this xi, right? This xi, right? Now you can combine these two together you can try to study some object like this, xi contract with this xi. Okay. This is called this is sometimes called the norm of this vector. Okay. This is called the norm of the vector. So xi, I has an index, right? So xi is a vector. Whenever this index is repeated, means it's summed over. Okay. You have to think about the sum over all the I. Okay. That's the meaning of I put this xi and this xi together. Okay. So this is called the norm. So you can think about this entire object under the rotation R. Okay. So under rotation, what happened for this composite object? So you can easily check yourself. You see, I have individual transformation for this and also this. Then you just put them together. Put them together. This becomes what? Becomes x. So this is x. Let me make this a very precise way. So what can I see? So okay. So this xi becomes this xjrtji, right? So first I will get xjrtji. Okay. Now for the second, I will have this one, right? Right. So the repeated index is summed over. So in order to distinguish with this j as a label j I already used. So I switch to another. I switch this j to k. Okay. So what I will get is here is r I k x k. Okay. That's what I have. Okay. Just honestly do it. Now calculate this one. So what is this? So think about for a few seconds, then you realize that you can do the product of these two first, okay? You see? This is just a metric products. Then the result I already give you, see? This is identity. Okay? R transport times R is identity there, okay? So here, what I have is nothing but x j. Identity, I can represent the identity as using delta, right? Using delta, right? So this is delta jk, and then xk, okay? You see? Delta means when k equals to j is 1, okay? So it's precisely identity, see? Represent identity matrix. So what is this? Since this is delta, this just gives this xj, xj. You see? So xj, and xi, they are the same, right? Because repeated index are summed over. Are summed. When it's summed, then doesn't matter you label it by I or j, right? That's the same thing. You see? Because it's appearing in this sum. So they are the same thing. So this means what? This means the property of this rotation matrix preserves this so-called norm of this vector, okay? Now inversely, I can use the preservation of the norm to define this rotation matrix. Is that clear? I forget about all the previous middle school exercise, okay? I just forget it, throw it away, okay? Just start from here. I want to search for some rotation which preserves this norm, okay? Then you see it? Then by demanding this preservation, okay? Demanding this norm is unchanged under this transformation, you will get this one will be equal to identity, you see? Then I can use that one, demanding that preservation to define the rotation matrix. Is that clear? So, so this provides a more elegant way to define this rotation matrix, okay? Because this just says, okay, rotation matrix preserves something, okay? if you find that something which is preserved, then it makes you to understand this rotation matrix deeper. Okay, you understand what it does? It preserves something. Okay. So similarly, we use this way to define the so-called Lorentz group or Lorentz transformation. Okay. Now the key point is we have to find something that looks like this, right? Which quantity is preserved under Lorentz transformation? Okay. So Lorentz transformation is defined in the same way. Defined as the same way. So what is that? So we have to think about a 4-dimensional, 3 + 1-dimensional space-time. In particular, we have a time. We have to find something is preserved under Lorentz transformation. If you could find that, then it makes you much easier to derive this Lorentz transformation. So what is that? We already know that, right? In Minkowski space-time, we often talk about a 4-vector, okay? You see, I switch the index. I don't use ijk. Now I use mu nu, blah, blah. Mu nu sigma, something like this, okay? So x mu is a 4-vector. 4-vector usually is labeling something like this, right? Okay? Labeling something. There's 4 components. This represents 3 components. Or if you want, this is t, x, I. Okay? Looks like this. See? So as said, we have to find the norm. So again, find the norm. So what is the norm? So this is the 4-vector in Minkowski space-time. What is the norm of this 4-vector? What is the norm of this one? 4-vector. So to define a norm, usually here we just make it super simple. We don't mention additional structure. We just say, okay, norm is defined this way. But if you are more careful, mathematically, in order to define a norm of this 4-vector, we have to introduce something called a metric, because metric does the job to contract these two. Okay, you see, very natural, right? Because this is a contraction, right? In principle, contract in what way? Okay, you can insert some more structures into this contraction, right? Because this guy contract with this guy, but metric tells you how to contract. Okay? Because this is a matrix insertion. You see? It's not a big deal, right? So indeed, in Minkowski space-time, this is sometimes also written in this way, but these two are just equivalent. I choose to present in this way in order to make this matrix product very, very clear, okay? In a very precise way, okay? But they are just the same. So this is what? So this is t squared minus x squared minus y squared minus z squared. See? Okay? This represents a 4-vector. If you want the distance for this, the norm of the 4-vector can also be interpreted as the distance from the origin to this point, right? This point, or some event if you want, okay? In special relativity, we call this the event, okay? The many event. Event 1-to-1 corresponding to a 4-vector, okay? You can make it start from the origin, okay, to construct a vector to point to some event. Then it offers you some 4 vectors, okay? Now this object measures the distance between this one and this one, okay? In special relativity or in Minkowski space-time. So this is the norm. Now we found the norm very good. Now we just stupidly follow this definition. Then you get it. Okay. So we are now trying to search for which transformation preserves this law. Now formally, let me write this transformation in this matrix form. For example, x means the vector, and transformation I do in this way. So x essentially the x mu, okay? Because from the very beginning, I choose using, where's my index notation? I erase it, okay. So I choose to using this kind of thing to represent a column vector, okay? And the upper index is a row vector, okay? So this is this one. I schematically write everything in terms of matrix form. So if the transformation send x to some matrix product with this x, then as I said, we have to preserve this norm. So let me also write this norm in terms of matrix form. So this is xt dot g is also matrix, and dot x. Okay. So this norm under this transformation, as you can see, was sent to x transpose, lambda transpose, and g, and then lambda, and then x, okay? All are the matrix, okay? Now this has to be, because norm has to be preserved, this has to be x transpose g x, which is the norm itself, right? By definition. Now from this equation you get some from this equation you throw away this xt and this x, then you get some simple equation, right? Which means this equals to this, right? See? Very simple. Okay. Now you find the defining equation for Lorentz transformation. It's very simple. Okay. This means that the Lorentz transformation is defined in this way, can be defined in this way. Is some matrix satisfy lambda transpose times g times lambda equals to g. That's it. You see? So this is the definition, mathematical definition for the Lorentz transformation. Okay. If you want, you just work it out. Okay. Then you find what is lambda. Then you work it out. This Lorentz transformation. So you may ask me, what is G in precise form? G is, if you write it in a matrix, G is just plus, minus, minus, minus. Okay? Okay? This is G. It's also very simple. Here I use the most minus signature for notation. You see, plus, minus. There's 3 minus, a single plus. This is G. Now, this is a true definition for Lorentz transformation, but down to earth, we have to work it out, and eventually we have to understand it. Okay. It's a bit of work, and so since many of you already learned the Lorentz group, so can you tell me how many independent group elements for the Lorentz group? How many? Can you guess? How many number? Just give me a number. How many? 6, good. Correct. Okay. There are 6 independent rotations, if you want, inside this Lorentz group. Okay. Any generic Lorentz transformation can be decomposed into these 6. Okay. Okay. So in other words, Lorentz group, Lorentz transformations can be decomposed into some more easier one or familiar ones. For example, the special rotations, okay? And there are also something called boosts, okay? There are 3 here, there are also 3 here, okay? 3 plus 3 is 6. Okay? 3 means there are 3 independent elements, okay? Why? Because, as I said, Lorentz group is some rotation in some 4-dimensional, right? 4-dimensional space, including time. Okay, so space-time, 4-dimensional space-time. Then, of course, if you don't touch time, purely rotation the 3 special direction. Okay, of course, belongs to the Lorentz transformation, right? If you don't touch time, okay. And we already know that's the 3-dimensional rotation group, right? Just 1 dimension higher compared with what we worked out, like the 2D special rotation group. Okay, something called SO3 if you want, right? Literally, it's from SO2 up to SO3. Okay, so SO3 is certainly a subgroup. It's a subgroup of Lorentz group. Is that clear? Right? Reasonably, right? So these 3 special rotations, if you want, it can be represented by a matrix in a very precise way. For example, if you want to rotate, you have x, y, z, okay? You have x, y, z. If you want to rotate around the x, which means you rotate y and z coordinates, right? 4 points. So this is one, this is what we just learned. Cosine, sine, and minus sine, cosine, right? Now, if you rotate around the y, means you only touch x and z coordinates, then this becomes cosine theta 1 minus sine theta, sine theta, and cosine theta, okay? Like this. Here, I just escaped the time coordinate, as you see, because this is a 3x3 matrix. But if you should think about it, these special rotations don't touch time. Okay, means that the time is just trivially add if you want a 4x4 matrix. Okay, just trivially add somewhere here. Okay, 1, don't touch means 1. Okay, the element is 1. Okay, and then this is 3x3. This is rotate x, y, z. Okay, rotate x, y, z. And similarly, r, z, theta will be the cosine, sine, minus sine, cosine, and 1. Okay. All other component which I didn't denote is just 0. Okay. So this is the rotational group. As that is a subgroup of the entire Lorentz group. Now there are 3 more boosts. Okay, boost. Boost means what? Do you know boost? You learn the special relativity, you should know boost, right? Boost means you add some velocity or speed along some direction, right? Right? Then you have another frame. For example, you can create another frame. Then there is a Lorentz transformation between these two. Okay, coordinates under different frames. Okay, this is called a boost. Okay, boost. So what is the transformation representing this boost? For example, if you want to boost along the x direction, often we use this beta parameter to represent the boost. Okay, boost. So this matrix is some cosh beta, sinh beta, and sinh cosh, and 1, 1. Okay, because the boost must have something to do with time, so we cannot escape, right? So this is the 4x4 matrix. It's a complete 4x4 matrix. So this is the boost. This is the boost in the x direction. Similarly, you can write down the boost in the along y or z directions. which I will just skip here. You can write down by yourself. So what is beta? So beta, the cosh beta is the related to the familiar boost velocity is 1 over square root of 1 minus v square, and v is the boost velocity. Okay. So v is related to beta. V is related to beta, and so this matrix gives you a transformation for a 4 vector. You just act this kind of matrix, okay? Act this matrix onto a 4 vector. It transforms one 4 vector to another, okay? Then it establishes the Lorentz boost or Lorentz transformations. For example, you can check yourself. This cosh beta is this one. Then for the x direction, you can work out how the coordinate after this Lorentz transformation is related to the previous one. This transformation is essentially just send this x to x plus vt, this one, and send t to 1 minus v squared t plus vt, vx. Okay. This is a familiar special relativity relation or boost relations. Okay. It's just represented by this matrix. Okay. Act this matrix on the 4 vector. You get it. Okay. Now we already mentioned that there is a subgroup of SO3. So for this reason, you see, we have three spatial directions and 1 time directions. And we also know the Lorentz transformation is some rotation. So following the previous notation about this 2D rotation group, which is SO2, now we call or we label this Lorentz group as SO1, 3. Okay. Okay. We put a comma here, and this is 1. This is 3. 1 means there is a time direction. Okay. There is a time direction. 3 means there are 3 spatial directions. Okay. Now you are rotated in this 4-dimensional space. Okay. Is that clear? So we put the SO1, 3. Okay. Put the 1, so 1, 3. Because why S? Because you can check for all these transformation matrix. You can check the determinant. The determinant is 1. Okay, you can check it yourself. Okay, determinant is 1. Now, this is not the entire story for the Lorentz group. Because if you accept, this is the original definition for the Lorentz group. If you are a careful person, you realize that there are more candidates for this lambda. Go beyond this property. Let's say determinant equals to 1 property. Okay. There are some other pieces. So mathematically, so far these 3 plus these 3 only represent the part of the entire Lorentz group. The part of the entire Lorentz group. Which part? The part is connected to the identity. Okay. If you learned some piece of group theory, you should know what I'm saying. Okay. So what I'm now trying to tell you now, this entire Lorentz group topologically has different disconnected pieces. Okay. Like 4 pieces. Okay. 1 piece is connected to the identity, which means what? Connected means what? Means this kind of transformations can be smoothly tuned to the trivial transformation, which is the identity, okay? But there are some group element which is not quite trivially connected to the identity, okay? Can you imagine that? But they also satisfy this good definition. So you should accept they are also belongs to the Lorentz group, right? I'm telling you now there are such kind of pieces, okay? Which we didn't touch now. If you want, you can work it out in your yourself. Mathematically, there's a well-known result. There are 4 pieces. Okay. The one piece we're talking now is the piece connected to this identity. Now, immediately the question you ask me is how can we jump to those pieces, right? This is a very good question. You see, the point is all these transformations are associated with some continuous parameter. You see, for example, this is theta. Theta is the angle, right? Okay, theta is the angle. It's a continuous parameter. You can change theta from 0 to 0.5 to blah blah to 100, right? That's what we mean by continuous parameter. It's continuous parameter. This beta is also right. You can change this beta, continuous tuning this beta. Okay, but now there are also some transformations which is called discrete transformations. Okay, discrete transformations. They cannot be represented by some continuous parameter. Okay, precisely because the existence of those discrete transformations. Now, if you add this discrete transformations on these pieces, then you jump to some other pieces. Is that clear? Picture-wise, clear? Okay. Because discrete means jump, right? It's not just smoothly go. It's just jump, suddenly jump. Okay. This means discrete. Okay. For example, there are something called let me take use of this space. There's something called a parity. Okay, parity or P transformation. This transformation send this T x y z goes to T minus x minus y minus z. Okay, you see? You see? It's very simple, right? Just flip the direction of all this x y z. Don't do anything else. Okay. You see, this kind of transformation does not belong to any of those. You see? Because it's discrete. These are just all the continuous. Okay. There's also a transformation called the time reversal. Or T. T transformation is, as you can imagine, just send this to minus T. Don't touch x, y, z. Okay? Don't touch x, y, z. Okay? You can check. These transformations satisfy this property. Can you check that? Easy, very easy, right? You can check it. So it's the element of the Lorentz group. Okay? But after that, it does not belong to these representations. Essentially because they are very special. They're just jumping. Okay. Now, precisely, you can work it out, but I don't have time. Since you have PT, let's say you have identity, you have P, you have T, you can also have PT. So in some sense, you have 4 independent combinations for this P and T. Okay, because PT are different. You can try to see identity, P, T, and PT are all different. Okay. Okay. Then combined with this discrete, this 4, one is trivial. Okay. Combined with these 4 discrete transformations together with this special piece. Okay. This piece connected to the identity. You can generate all the Lorentz group. Okay. There are 4 patches. Okay. Very natural. You can check yourself. Are there any questions about this derivation of this Lorentz group? So we introduced the Lorentz transformations, but the eventual purpose is try to understand the object, right? Those physical objects like fields or something, they transform under Lorentz transformations, okay? So it's better to classify how objects transform differently under Lorentz transformations, okay? So how classification of objects. For example, we can call something scalar. Scalar essentially means they're just unchanged or invariant. If some object is invariant under Lorentz transformation, then we call it scalar. Okay? Can you find some scalar? This is the scalar, right? Entire thing, you see? Under Lorentz transformation, this does not change, okay? So we call something vector if it transforms in this way. For example, x mu. We know x mu is a vector, right? We know x mu is a vector. So x mu under Lorentz transformation, as we just discussed, is transformed in this way. Okay? If some object is transformed in this way, we call it a vector. It's a Lorentz vector. Okay? Now there are also tensor, Lorentz tensor. For example, T u nu. If some object transform in a slightly more complicated way, looks like this. Okay? Under Lorentz transformation, then we call it a tensor. So lambda is something already known, right? We just work it out, right? If you can specify which Lorentz transformation you are talking about, we know precisely what is lambda, right? Lambda is that lambda, okay? Lambda represents which Lorentz transformation you are talking about. Now I'm telling you, depend on how the object transforms under Lorentz transformations, we classify different objects, okay? For instance, Lorentz scalar, Lorentz vector, and Lorentz tensor. See? You can just check yourself some familiar object, whether this is a scalar, is a vector, or tensor. Right? Just, yeah, using this property. Just check whether it's transforming this way. It's not a big deal, right? It's just give some names if you want. Yeah, I just name this as scalar, name this as vector, name this as tensor. That's it. Now, if you accept this terminology or the name or classification, then you can easily find for example, for a vector, for a very general vector, V mu, for a vector V mu, yeah, sometimes we put the index lower, sometimes upper. It doesn't really matter. But the point is that this, if the vector, we already introduced the definition of such kind of thing, right? We call this is a norm, right? Call this is a norm. If the norm is positive, for example, if the norm is positive, we call such vector time-like. Why? Why give such a funny name? Check yourself. Here, right? If you set x, y, z are all 0, only a single t, okay? This is positive, you see? So if the normal vector is positive, we call it time-like. Time-like means what? It looks like a time, okay? It looks like a time, okay? That's time-like. The oppositely, if the norm of some given vector is negative, we call it space-like. Then naturally you ask, what if it equals 0? What's the name? What's the name? Equals to 0. less than 0 is space-like, no? Very good. Very good. Like. Okay, just a few lanes. Okay, not a big deal. Okay. Now, through this course, how much time we do have? We only have like more than 10 minutes. Through this course, we are going to deal with fields, of course, right? So as you can see, here we don't touch yet fields, okay? We don't make this kind of vector or tensor as a function of space-time, right? So still, this is just a simple classification of some tensors. But eventually, we can promote it to fields, okay? Then you can classify scalar fields, vector fields, tensor fields, okay? We're going to do it later, but not today. But definitely we'll come back to this classification when we talk about different types of fields. It's not a big deal. So last 10 minutes or 12 minutes, we have to discuss another important one. As promised, we finished spectral relativity review, okay? Review. I'm just going to review for you the part of the spectral relativity, which is Lorentz group. In the following 10 minutes, I'm going to review of quantum mechanics to tell you how to quantize the harmonic oscillator, okay? In case you already forgot your quantum mechanics and also spectral relativity, this is the essential, okay? So harmonic oscillators, do you know how to define harmonic oscillator? What is harmonic oscillator? What is harmonic oscillator? Harmonic oscillator is just something, there's a spring, right? There's an object, right? Okay? This is harmonic oscillator, you know? So, we can write down an equation of motion for this harmonic oscillator. What is that? If the mass is m, if this position is x, if the position is x, then equation of motion has the double dot for time, okay? Plus kx equals to 0, okay? K is the coefficient. K is the coefficient that come from where? Yes? Come from the Hooke's law, okay? So there's a force coming from the spring, okay? According to Hooke, you have a kx, okay? Now, this equation of motion, we can rewrite it a little bit. Let's say x double dot plus omega square x for convenience. Now, omega is defined as square root k over m. Is that okay? Now, this equation is the second differential equation. You should be able to work it out. What is the solution for this second order differential equation? Cosine and sine, very good. So the solution is that xt immediately you can guess if it's some cosine combined with sine omega t, okay, with some unfixed coefficient a and b, okay. You can easily check. This is the solution. This is the solution indeed, right? This is the solution. Now, for normalization or for later purpose, let's just rewrite a little bit in some funny way, but it doesn't really matter. Let's extract some overall coefficient here and leave some coefficient a and a star here. We all know cosine and sine can be related with this complex exponential, right? Right? This exponential minus I omega t and exponential I omega t. Okay? Is that okay? Now there are some coefficient, because there are some coefficient, right? I just transform it into some other coefficient. Now we extract some overall numeric. That's okay, right? Just some normalization. You define. You can treat this as your definition of your A and A star. Now A and A star are conjugate with each other, you see, in this form. Why? Can you tell me why? Yes. Who said the correct answer? I'm sorry. Yeah, very good. Because this is real, okay? This is real, so this has to be A star, okay, for this A. You can check, because you take complex conjugate, it goes back to itself. Okay. Otherwise, it does not. Now, we have to quantize this harmonic oscillator, okay? We have to quantize this harmonic oscillator. As said in the very beginning, quantization means make the classical variable to quantum variable, right? In particular, in Heisenberg picture, the way to quantize this system is just to make this xt, make it become some operator, okay? Because Heisenberg picture allows the operator depends on time. Clear? Now, if you could do this job, then you finish the quantization very easily, okay? Okay, now question is how to do it. We have all the mathematics. How can I make this as an operator? That's my question. Okay. Now look at the solution, because this is already solution is already there. Just look at solution. Look at the solution. This m and omega are parameters. Okay. No way to quantize it. It's a parameter. Okay. It's not a variable. Okay. No way. Time, we know there's no way to quantize time. Okay. This is omega. So apart from this A and A star, nothing you can quantize. Okay. So the correct way to promote this xt into an operator, the unique way to do this is just make this A and A star operators. So we make this A as A hat and A star as A hat. Because this is an operator, we use some alternative notation in the dagger. Okay. Okay. Because dagger means the conjugate for an operator. So that's it. Okay. This is the quantization. That's it. Now what? As we know, I mean, this is so cheap. Maybe for some of you, they say this is too cheap. Quantization in my QM course. Whenever I was told to do a quantization system, I have to work very hard to quantize my Schrodinger, work out my Schrodinger equation and blah blah blah. Solve some energy levels. But for this one, it's really simple. It's almost finished. Okay, it's almost finished. Now, if you accept this. Now you can easily justify yourself the usual or ordinary quantization condition. Don't forget the quantization condition, okay? The usual quantization condition, which my rating as this equal time commutator for x hat and the p hat. Because I already now have x hat, okay? There, you see? Now I have my x hat. Now x hat, from x hat you can also work out your p hat, because p hat is defined as the m x hat t dot, okay? Because it's the mass times the velocity, right? So this is the p. So p is known. So you can check x and the p commutators. You can check yourself this commutator equals to I, which is the ordinary quantization condition, or canonical quantization condition, whatever you want. Then this equation is equivalent, or from this equation you can derive the commutator for this A and A dagger. This equals to 1. Okay? These two are just equivalent. Then from here, then it's really done. Okay. So impose this quantization condition combined with the promotion of the original function now to the operators. That's it. Okay. This is the quantization. It's a cheap quantization in Heisenberg picture for harmonic oscillators. Okay. It's done. Why I say it's done? Because when I have after I have these commutation relations, I can build up my Hilbert space. Okay, I can build up my Hilbert space. So what is my Hilbert space in this case? So the Hilbert space. Don't try to use this one. Maybe I can make some space. Okay, here. So where is my Hilbert space? In order to build up my Hilbert space, I have to first define my ground state, okay, or vacuum state, which is this one, okay. So my vacuum state is defined by this equation, okay. It's defined by this equation. My vacuum state is defined by killed by this A hat, okay, not A dagger, but A hat. This is defined by vacuum. Now you can justify yourself. Then from here, you can generate a lot of higher mode state. For example, I can generate some state that looks like this, n state, which is generated by you act A dagger n times above on this vacuum. Okay, this gives you n mode state. Okay, or higher n state. Okay. You can also check this state certified this orthogonal condition. This is just MN. Okay, and you can define like what you learned in your quantum mechanics course. You can define something called number operator. N hat. N hat is A dagger A. Okay, A dagger A. Then you can check A. Why we call this is a small n, because you act on this n on this state. You find that this is the eigenstate. Okay. This is the eigenstate. The eigenvalue is just n. So this is the n mode state. Okay, the n mode state. And what else? You can also write down, check some. I mean, the system is basically already quantized over. You can check whatever you want. Okay, here. For example, you can check Hamiltonian. We haven't yet written down Hamiltonian, but Hamiltonian is just given by this. P square over 2m plus half m omega square x hat square. This is the energy. You see, this is the energy, total energy. So this is Hamiltonian, and you can check the. This can also be written as the omega a dagger a plus half. Okay. Many things. You can also check for any time dependent here. Here we do have time dependence. For example, in x t hat, right? Now we promote it to the hat. We promote to the x t. You can check the Hamiltonian generated time evolutions. What do I mean by that? You can check for example, the nice equation. For example, a hat t or x, doesn't matter, x hat t dt. This is nothing but the commutator x hat t, commutator with the h. H is what I write here, h, okay? The point is, now all the physical quantities can be expressed in terms of x and p. And I know precisely how x and p expressed in terms of A and A dagger, okay? So through the A dagger commutation relation, I can work out all the possible commutation relation, right? So you can check h, this x hat commuted with h is indeed the time derivative act on this variable, okay? Or this quantity. This means what? This means the Hamiltonian generates time evolution, you see? Okay? Okay, so yeah, we basically finished the content today. Yeah, we finished. Yeah. Okay, 下课。
度位器它是一个标量还是一个张量？它又是不变的，它又
Follow the definition. Check 它定义。
它两个定义都，它的标量是不变的，它是一个莫伦是不变的。
哎，你猜到了吗？看看这个。
变换的定义是这样写的。说明 G 是一个洛伦兹不变量，然后这个变换又刚好是 tensor 的定义，所以它既是 tensor 又是 scalar， 是不是这个意思？
你在说什么啊？什么叫It's a good question. No, certainly it's not a tensor. Why call it a tensor? 为什么说是 tensor？
话筒会 被正确放置。话筒被正确放置。话筒被正确放置。话筒被正确放置。话筒被正确放置。
这个说到你的